What if the greatest engineering marvels of the ancient world weren't built by chance, but designed by master architects whose names we'll never know? Think about the pyramids of Giza, standing for thousands of years with precision that still astonishes engineers today, or the mysterious stone walls of Sacsayhuaman in Peru, where massive boulders fit together so perfectly you can't slide a piece of paper between them. These aren't just random constructions, they're the work of brilliant minds who understood mathematics, physics, and design on a level that sometimes rivals our own modern knowledge. Yet history has forgotten them, leaving behind only their incredible creations and a haunting question: who were these architects, and how did they achieve what seems nearly impossible even with today's technology? Welcome to a journey through time where we explore the hidden blueprints and lost designs of civilizations long gone. These ancient plans, etched on clay tablets, carved into temple walls, or passed down through cryptic symbols, reveal a world of innovation and sophistication that challenges everything we thought we knew about early human achievement. From complex hydraulic systems that managed water with breathtaking efficiency to architectural designs that aligned perfectly with celestial events, these blueprints show us that ancient engineers weren't just builders, they were visionaries. They dreamed on a scale that still inspires awe, and their work continues to influence how we think about design, sustainability, and the very limits of human capability. As we delve into the mysteries of these forgotten masterminds, we'll uncover how their revolutionary ideas might hold answers to some of history's greatest puzzles. Why did certain ancient structures survive earthquakes that leveled modern cities? How did they move stones weighing hundreds of tons without machinery we would recognize today? And what can these ancient techniques teach us about solving our own contemporary engineering challenges? This exploration isn't just about looking back, it's about rediscovering knowledge that could shape our future. So join me as we decode the secrets of the architects that never were, and embark on an adventure that will forever change how you see human history and the incredible power of imagination. This idea of lost civil engineering forces us to confront a fascinating and sometimes uncomfortable question. How could cultures that lacked steel, concrete, and powered machinery achieve what seems to demand precisely those things? It's the architectural equivalent of finding a smartphone in a medieval castle. These structures aren't just old, they represent a profound anomaly, a spike on the graph of human technological progress that doesn't neatly connect to the timelines we've constructed. For a long time, the prevailing assumption was that these were simply trial and error projects, built over generations by vast armies of laborers. But that explanation is starting to crumble under the weight of the evidence. Consider the sheer precision. The Great Pyramid of Giza is not just a pile of rocks. Its base is almost a perfect square, with sides aligned to the 4 cardinal directions with an error margin of less than a single degree. The stones themselves were cut and placed with such accuracy that the gaps between them are often less than a millimeter. This isn't just brute force, this is a level of surveying, mathematics, and quality control that implies a deep, formalized knowledge. It suggests the existence of master planners, architects who worked from detailed blueprints and specifications, not just rough sketches in the sand. Then there's the application of advanced physics, often hidden in plain sight. Look at the ancient temples and pagodas across Asia, particularly in Japan and China. For centuries, they've withstood violent earthquakes that have flattened modern cities. Their secret, a brilliant form of passive seismic damping. Builders used complex, interlocking wooden joints that flex and absorb energy, rather than rigid connections that would snap. They also employed massive, heavy roofs that acted as a counterweight, stabilizing the entire structure during a tremor. This is sophisticated engineering, a conscious design for resilience that we now emulate in our own skyscrapers with base isolators and tuned mass dampers. They understood the principles of dynamics in a way we only formally discovered much later. Perhaps the most compelling aspect of this lost knowledge is its disappearance. The Roman concrete used to build the Pantheon, which has endured for 2 millennia, famously became a lost recipe after the empire's fall. Medieval and even Renaissance builders couldn't replicate its durability. We've only recently begun to unravel its secrets, discovering that the incorporation of volcanic ash created a chemical reaction that actually strengthens the material over time, especially in salt water. This points to a pattern. Engineering knowledge isn't always a steady, upward climb. It can be fragile, tied to specific cultures, and vulnerable to war, social collapse, or simply the passage of time. The architects and their detailed manuals vanish, leaving behind only their indestructible monuments as silent, enigmatic proof of what was once known. So where do we even begin to understand the minds behind these marvels? The answer lies in the very documents they left behind, but to call them simple blueprints is a profound understatement. These ancient plans are intricate technical manuscripts, dense with data that would feel right at home on a modern engineer's desk. Imagine unrolling a papyrus scroll in ancient Egypt and finding not just a drawing of a temple, but a full set of specifications, the exact type of limestone for the foundation, the precise angle for the corridor to capture the sunrise on the summer solstice, and the sequence for laying each course of stone to ensure perfect weight distribution. This wasn't art, it was applied science. One of the most stunning examples comes from Mesopotamia, where clay tablets detail the construction of elaborate irrigation canals. These aren't just maps of ditches, they include incredibly precise calculations for water flow rates, the optimal slopes to prevent erosion or siltation, and specifications for the gates that would control flooding. The architects clearly understood hydraulic principles we associate with much later periods. They calculated volume and velocity, designing systems that could sustain entire cities in an arid environment. This shows a predictive, mathematical mind at work, not just someone experimenting with mud and water. The depth of planning extended far beyond the practical. In Egypt, the layout of a temple was a cosmological statement. Blueprints, often etched onto temple walls themselves or on polished limestone flakes known as ostraca, integrated celestial alignments with architectural form. The positioning of a doorway, the length of a hallway, the height of a column. Each element was often tied to a star or a planetary movement. This means the architect had to be a master of geometry, astronomy, and theology simultaneously. The blueprint was a bridge between the earth and the heavens, a set of instructions for building a machine for worship that operated on both a physical and a spiritual level. This level of sophistication forces a huge question. How was this complex, multidisciplinary knowledge passed down? The existence of such detailed plans suggests a formalized system of education, a way to teach the next generation of master builders. There must have been schools or apprenticeships where these principles, the math, the material science, the astronomy, were diligently recorded and taught. The precision we see across centuries, even millennia, in structures from the same culture implies a robust system of knowledge transfer. It wasn't just one genius, it was an entire tradition of genius. And then for so many of these cultures, that chain was broken. The libraries that housed these manuals burned, the guilds of builders disbanded, the language to read the formulas was forgotten. We are left with the magnificent, silent buildings and the ghostly outlines of the blueprints, the stark evidence of a greatness that was achieved, lost, and is only now being slowly rediscovered. And if we want to talk about a discovery that truly shattered our perception of ancient innovation, we have to turn our attention to the bottom of the sea. In the early 1900s, sponge divers off the coast of the Greek island of Antikythira stumbled upon a shipwreck, a Roman cargo vessel laden with treasures. Among the statues and pottery, they recovered a lump of corroded bronze and wood that seemed unremarkable at first. It was only years later, when an archaeologist noticed precisely cut gear wheels embedded in the rock-like mass, that the world realized it had found something extraordinary. This object, now known as the Antikythera Mechanism, is arguably the most stunning archaeological find of the 20th century, not for its gold or jewels, but for the profound and advanced intellect it represents. This wasn't a simple navigational tool or a decorative item. Through painstaking analysis using modern X-ray and CT scanning technology, scientists have been able to peer inside the calcified layers and digitally reconstruct the device's inner workings. What emerged was nothing short of an ancient analog computer of breathtaking complexity. It contained over 30 meshing bronze gears, precisely calibrated to model the motions of the sun, the moon, and the known planets. By turning a hand crank on the side, the operator could advance or reverse time, predicting celestial events like eclipses with remarkable accuracy. It even accounted for the subtle irregularities in the moon's orbit, a concept known as orbital eccentricity, which requires a very sophisticated understanding of astronomy and mathematics. The true genius, however, is revealed in the theoretical blueprints that researchers have had to reconstruct from the fragments. The original design plans, likely drawn on papyrus or parchment, were lost to the sea centuries ago. But the machine itself is a physical manifestation of those lost blueprints. Reverse engineering its logic has shown that the anonymous inventor used a system of gears that we now call a differential gear. This is not a simple component. It's a mechanism that calculates a specific function, in this case, the phase of the moon by comparing the relative positions of the sun and moon. For context, this exact same principle is fundamental to the operation of a modern automobile, allowing the wheels to rotate at different speeds while turning a corner. Yet here it was in a device crafted 2,000 years before the automobile was even a concept. This single artifact forces a complete re-evaluation of an entire era. It tells us that in the 2nd or 1st century before the Common Era, there existed a genius, or more likely, a school of thinkers, with a grasp of mechanics, astronomy, and manufacturing that we simply did not attribute to that time. The precision required to cut these tiny metal gears, some with teeth just a millimeter long, implies the existence of specialized tools and techniques for fine metalworking that are otherwise absent from the archaeological record. The Antikythera mechanism wasn't magic. It was the product of a highly developed technological tradition, one that clearly had design manuals, mathematical formulas, and a theoretical framework for building such incredible machines. Its discovery is a powerful reminder of the fragility of knowledge. This one device survived by chance, encased in a shipwreck that preserved it from the elements that destroyed its sister devices and the libraries that housed its instructions. It stands as a lonely, magnificent data point, a spike on the graph of human achievement that suggests an entire lineage of complex technology that was lost, perhaps for centuries. It challenges the very linear narrative of progress we so often take for granted, proving that brilliance can flare up, achieve the seemingly impossible, and then vanish, leaving behind only a corroded clue at the bottom of the ocean, waiting for a future generation to decipher its secrets. This reliance on a coded language of construction becomes even more fascinating when we move from the grand temples of Egypt to the mountainous realms of the Inca. Their architectural triumph wasn't just in the impossibly precise stonework of Machu Picchu or the fortress of Sacsayhuaman, but in how they might have encoded the very instructions for building them. Unlike the Egyptians, the Inca left behind no written language as we know it. Instead, they used the quipu, a complex system of knotted strings. For a long time, these were believed to be simple accounting tools, a way to record quantities of grain or numbers of llamas. But the discovery of far more complex quipu, with hundreds of strings in a multitude of colors, materials, and knot types, has led to a revolutionary hypothesis. What if these were not just ledgers but blueprints? Imagine a master architect, a man the Inca called a Quechua Kamayoc, or specialist in knots, meticulously tying a series of strings. The color of a cord might not represent a commodity, but a specific type of stone granite, andesite, limestone. The type of knot, a figure 8, a long knot with a specific number of turns, could encode a measurement, perhaps a length or an angle. The position of that knot on the string might indicate where in the construction sequence that particular stone was to be placed. This system could have been a portable, durable, and incredibly efficient way to transmit the complex structural data needed to assemble a building designed to withstand the violent earthquakes of the Andes. The interlocking jigsaw puzzle nature of their masonry, which allowed walls to dance during a tremor and then settle back into place, would have required immense precision in the cutting of each individual block. A quipu could have been the instruction manual for the stonemasons, a literal string of code defining the unique shape and placement for every single stone. The implications of this are staggering. It suggests a formalized, scientific approach to engineering that was so advanced. Its entire knowledge base was stored not in vast libraries of parchment, but in a compact, three-dimensional binary code of knots. This wasn't just record keeping, it was data storage. The loss of the ability to read the full quipu after the Spanish conquest and the collapse of the Inca state represents one of the most catastrophic data losses in human history. We are left with the physical buildings, the output, but we've lost the software, the operating code that told them how to build it. This pattern of encrypted knowledge repeats itself across the ancient world, pointing to the existence of a professional class of architect-engineers who guarded their secrets closely. In medieval Europe, the master builders of the great Gothic cathedrals operated through guilds, which were intensely secretive societies. Their advanced understanding of geometry, structural load, and the properties of materials was considered such powerful and valuable intellectual property that it was often encoded in the very buildings they created, hidden in the geometric patterns of the rose windows or the layout of the floor plans, accessible only to those initiated into their mysteries. This secrecy was a form of job security, but it also made the knowledge incredibly vulnerable. If a guild failed to pass on its secrets to a new generation, or if its members were dispersed by war or plague, that knowledge could vanish overnight, leaving behind a magnificent but utterly mysterious cathedral that later generations could only marvel at, unable to replicate. These symbols and codes were the lifeblood of ancient engineering, the critical link between a visionary idea and its physical manifestation in stone and mortar. Their silence today is our greatest mystery. This reliance on secretive guilds and encoded physical blueprints reveals a broader truth about ancient engineering. Some of the most vital knowledge was never written down at all. In a world before widespread literacy and standardized printing, the human voice and the master-apprentice relationship were the primary hard drives for storing complex information. This system of oral tradition wasn't a primitive fallback. It was a highly sophisticated and deliberate method of knowledge transfer, perfectly tailored to protect the most valuable and sacred techniques of a trade. Think of it not as a library that could be burned, but as a living, breathing database, constantly updated and refined, but only accessible to those with the right password initiation into the craft. The master builders of the great Gothic cathedrals are a perfect case study. For centuries, they engineered structures that reached for the heavens with seemingly impossible lightness and grace. The flying buttress, the ribbed vault, the precise distribution of weight and thrust, these were revolutionary concepts that defied gravity itself. And yet, we find almost no detailed written plans or technical manuals from the period explaining the underlying math and physics. How was this done? The knowledge was passed from master to apprentice on the scaffolding itself, whispered in the dust-filled air of the workshop. A seasoned builder would teach a young initiate how to calculate a curve using a simple piece of string and a nail, a method that encoded complex geometric principles into a simple, repeatable action. The proportions of a window, the angle of an arch, the mix for a stronger mortar, these were not written in books but memorized through songs, chants, and rhyming couplets, making them easier to recall and less likely to be altered. This oral code ensured that the guild's most powerful secrets remained within the guild, creating a monopoly on skills that were literally awe-inspiring. This method explains one of the great mysteries of architectural history, the apparent sudden appearance of advanced techniques. When a flying buttress shows up in a cathedral's design, it looks like a spontaneous leap of genius. But in reality, it was likely the culmination of generations of incremental experimentation and problem-solving, all preserved and refined through oral tradition. Each master added his own insights to the collective knowledge pool, which was then verbally bequeathed to his successors. The blueprint existed not on parchment, but in the collective memory of the guild, a living repository of engineering data. This system was incredibly effective for preserving continuity within a stable culture, but it had a critical weakness. It was terrifyingly fragile. The chain of transmission was a single, thin thread. A plague that wiped out a guild's elders, a war that scattered its members, or simply the failure of a master to find a worthy apprentice could sever that thread forever. The knowledge didn't fade away. It vanished in an instant, leaving behind a magnificent building whose structural secrets became an unsolvable puzzle for later historians. This vulnerability is what makes the loss of so much ancient engineering knowledge so profound. We can reverse engineer the stonework of the Inca, but we can never recover the specific songs that taught a stonemason how to select and fit a stone. We can analyze the Roman concrete of the Pantheon, but we can't hear the exact recipe chanted by a foreman on a bustling Italian worksite. The oral tradition was the context, the why behind the what. It contained the nuances, the troubleshooting tips, the stories of past failures that taught what not to do. When that tradition died, all that remained was the physical object, the output, stripped of the rich human narrative that explained its creation. We are left staring at the incredible final exam, but the centuries of lectures and study groups that made it possible are lost to silence, a permanent gap in our understanding of how humanity first learned to shape the world. This obsession with geometric precision wasn't just about creating impressive monuments. It was a practical necessity for the most ambitious civil engineering projects of the ancient world. Consider the Roman aqueducts, those magnificent arteries of stone that carried fresh water across vast distances into the heart of cities. To achieve a steady, reliable flow of water, the gradient of the channel had to be meticulously consistent, often dropping only a few centimeters for every kilometer of length. Over a distance of 50 kilometers, a miscalculation of even a single degree in slope could mean the water would either flow too slowly and stagnate, or rush with such force that it would erode the channel walls and destroy the entire structure. The blueprint for such a project wasn't just a drawing. It was a massive topographical survey, a continuous elevation map that required an incredibly sophisticated understanding of geometry and land measurement to execute perfectly. The question of how they achieved this leads us directly to a fascinating gap in the historical record: the tools. We know the Romans had the groma, a simple cross-shaped instrument for sighting right angles, and the chorobates, a long, water-level table for checking gradients. But the precision evident in their longest aqueducts suggests they might have possessed something more advanced, perhaps an early form of the dioptra, a precision surveying instrument that could measure horizontal and vertical angles. Imagine a master surveyor, the librator, setting up this device on a hilltop. He would have been working from a detailed plan, using his tool to meticulously plot a course across valleys and through mountains, ensuring his team of laborers dug and built to an exacting standard that was dictated by mathematics, not guesswork. The existence of such advanced tools, even if no complete examples have survived, is implied by the sheer perfection of the finished product. They were working from a set of theoretical principles and practical instruments that we are only just beginning to appreciate. This level of accuracy becomes even more astonishing when we look at celestial alignments. The Great Pyramid's near-perfect alignment to the cardinal directions is not a happy accident. To achieve this, ancient Egyptian architects would have needed a method to find true north with incredible accuracy, long before the magnetic compass was available. One compelling theory suggests they used a method called the Indian Circle. An astronomer would track the path of a single star throughout the night, marking its positions on the horizon at the eastern and western extremes of its journey. By bisecting the angle between these 2 points, they could find a true north-south line with an error margin of less than 1/100th of a single degree. This process transforms the pyramid's blueprint from a simple architectural plan into a frozen astronomical observation, a permanent record of the night sky etched in stone. The architect here was not just a builder, but a scientist conducting a grand experiment in concrete and limestone. This systematic approach to measurement fundamentally challenges the traditional, linear narrative of technological progress, which often assumes that older means simpler. The evidence written into the landscape by these ancient engineers tells a different story, one of brilliant, localized peaks of innovation. They developed the precise tools and mathematical concepts they needed to solve the specific, monumental problems they faced. Their blueprint was a convergence of theory and practice, a document that encoded not only the physical dimensions of a structure, but also the advanced scientific understanding required to make it stand. The fact that these instruments and techniques seem to disappear from the record for centuries after is not a sign of their primitiveness, but a testament to the fragile and specialized nature of high knowledge in the ancient world. It was a flame that could burn brightly in one place and time, only to be temporarily lost, waiting to be reignited by a future generation rediscovering the blueprints of the past. This deep understanding of materials wasn't just about selecting the right rock or the strongest wood. It extended into a form of ancient chemistry that feels almost miraculous. The most famous example is without a doubt Roman concrete. While medieval builders struggled to create structures that would last a century, the Romans were pouring a material that has not only survived for 2 millennia, but has actually gotten stronger over time. Their blueprints and construction manuals, like those written by the architect Vitruvius, didn't just say, use concrete. They provided specific, almost recipe-like instructions. Vitruvius details the precise proportions of lime, volcanic ash, and aggregates, and crucially, he specifies that the ash must come from the town of Pozzuoli near Naples. We now know this wasn't arbitrary, it was empirical materials science. The volcanic ash from that specific region is rich in aluminous tobamorite, a rare mineral that forms long, plate-like crystals. When seawater slowly percolates through the concrete, it reacts with the lime and this special ash, causing the crystals to grow and interlock, filling in any micro cracks and actually strengthening the matrix. The Roman architects weren't just builders, they were master chemists who understood, through centuries of observation and experimentation, how to create a self-healing material. This sophistication with material properties extended far beyond the Roman world. In ancient Greece, the blueprints for majestic temples like the Parthenon called for the use of iron clamps to hold massive marble blocks together. But the architects demonstrated a profound understanding of metallurgy and environmental science. They didn't just use raw iron, which would rust, expand, and shatter the very stone it was meant to secure. Instead, the plans specified that the clamps should be poured in place using molten lead. The masons would carve a channel in the two adjoining stones, place an iron bar inside, and then pour liquid lead over it, creating a waterproof, non-corrosive seal that acted as a cushion, absorbing seismic shocks. This shows an incredible grasp of the galvanic series, the principle that certain metals can protect others from corrosion centuries before it was formally defined. They knew that lead would sacrificially protect the iron, ensuring the structural integrity of the building for ages. Perhaps even more intriguing are the materials that appear in legends and fragmented texts, hinting at knowledge that was completely lost. The Greek historian Herodotus describes the process of building the Great Pyramids, claiming the stones were lifted into place using machines made of short planks of wood. This vague description has puzzled historians for centuries. What kind of simple wooden machine could possibly lift blocks weighing several tons? Some modern engineers have theorized it might describe a sophisticated, multi-part lever system or an early form of the shaduf, a counterweighted lift. The blueprint for such a device would be a priceless window into their mechanical genius, but the knowledge of its exact construction and operation vanished. Similarly, ancient Indian texts on architecture, the Vastu Shastras, describe a type of waterproofing cement made from a complex mixture of fruit resins, plant sap, and other organic compounds. The formulas read like alchemical recipes, but they likely produced highly effective sealants that have since been lost to time, their precise chemical compositions forgotten. These examples point to a vast, distributed body of material knowledge, where each civilization developed its own advanced formulas and techniques, much of which evaporated when those cultures declined or were conquered, leaving us with only the enduring, silent testimony of their indestructible buildings. This seamless fusion of the heavens and the earth finds one of its most profound expressions in the very foundations of ancient cities, where entire urban plans were laid out as mirrors of the cosmos. The ancient Egyptians didn't just orient a single temple, they often designed their entire necropolises, their cities of the dead, as precise terrestrial maps of the celestial realm. The three pyramids at Giza, for instance, are not arranged in a simple line or a perfect triangle as one might expect. Their complex layout is now understood by many archaeologists to be a deliberate and incredibly accurate reflection of the three stars that form Orion's belt in the constellation Orion, a figure intimately associated with Osiris, the god of the afterlife. The blueprint for this vast funerary complex, therefore, was not merely an architectural drawing for quarrying and moving stone. It was a star chart of immense scale, a permanent gateway between the world of the living and the kingdom of the dead, set in limestone and granite. Achieving this level of celestial mimicry required more than just glancing at the night sky. It demanded a rigorous scientific process of observation and calculation that was almost certainly formalized in their planning documents. For a massive structure like the Great Pyramid, aligning its four faces to the four cardinal directions with an error of less than a 16th of a single degree is an astonishing feat of precision engineering. The prevailing theory suggests the Egyptian master builders used a method known as the Indian circle. They would have carefully tracked the rising and setting points of a single star over the course of a night, marking its arc on a circular wall or a cleared area of desert. By bisecting the angle between these two extreme points on the horizon, they could find a true north-south axis with breathtaking accuracy. This meticulous observational data would have been the first and most critical line drawn on their blueprints, the absolute foundation upon which the entire multi-generational project depended. The architect was first and foremost an astronomer. This tradition of embedding cosmic order into construction is a global phenomenon, appearing independently in cultures separated by vast oceans and millennia. Across the Atlantic, the great Mayan city of Chichen Itza on the Yucatan Peninsula is a masterpiece of astro-architecture. The step pyramid known as El Castillo is designed with 4 stairways, each with 91 steps, which together with the shared top platform equal the 365 days of the solar year. But its true genius is revealed during the spring and autumn equinoxes. As the sun sets on these 2 days, the interplay of light and shadow on the northwest corner of the pyramid creates a series of triangular shapes that slither down the balustrade, culminating in a stone serpent's head at the base. This effect produces the stunning illusion of a massive feathered serpent, the god Kukulkan, descending from the heavens to the earth. The blueprint for this structure had to account for the exact latitude, the precise angle of the sun at that latitude on those specific days, and the precise dimensions and angles of every single step to create this perfect visual spectacle. This was a calculated, predictable, and repeatable astronomical event engineered in stone. What does this tell us about the people behind these plans? They were not mere builders or stonemasons taking direction. They were a hybrid class of philosopher-scientists, individuals who held a unified view of the world where science, religion, and art were inseparable. The ability to predict a solar eclipse or the helical rising of a star was not just an academic exercise. It was a demonstration of divine favor and a means of maintaining social and political order by proving a connection to the gods. The blueprint was their tool of power and knowledge. It encoded their understanding of mathematics for calculating angles, physics for ensuring structural stability, and astronomy for dictating alignment, all while serving a higher spiritual purpose. This systematic, repeatable integration of complex fields points to a formalized and highly advanced educational tradition, a lost school of thought that saw the universe as an orderly, measurable system and saw its replication on Earth as the highest form of human achievement. The ruins we study today are the physical remnants of that profound intellectual tradition. This mastery of water wasn't just about grand, visible monuments like aqueducts. It thrived underground in one of the most sustainable and ingenious civil engineering systems ever conceived, the Persian Khanate. Imagine teams of surveyors working over 1,000 years before the Common Era, plotting a subterranean water network across the arid landscape. Their blueprints weren't drawn on paper, but etched into the land itself through a profound understanding of geography and physics. The process began by identifying a water source at the base of a mountain. Then, with astonishing accuracy, they would tunnel straight back into the aquifer, but that was only the start. The true genius was in the gently sloping channel they would then dig from the thirsty plains below, back up to meet this mother well. This precise, minimal gradient, often a drop of only a single meter per kilometer of length, allowed gravity to do the work, pulling the water silently and efficiently through the dark earth to the surface many miles away without a single pump. The plans for these systems reveal a level of foresight that feels almost modern. Vertical access shafts were dug at regular intervals along the tunnel's path, not only for removing excavated earth, but to provide crucial ventilation for the workers and, once operational, for maintenance and cleaning. The placement and spacing of these shafts were calculated to ensure airflow and structural stability, turning the entire Qanat into a living, breathing organism. This wasn't trial and error. It was a meticulously planned underground infrastructure project. The knowledge required to execute this was immense. The surveyors, known as mukanis, had to possess an intuitive grasp of hydrology to locate the aquifers, the geometry to plot the perfect slope over vast distances, and the geology to tunnel through stable strata. They were the unsung hydraulic engineers of their day, and their hidden blueprints provided lifeblood to desert cities for centuries, creating flourishing oases in the most unlikely places. This sophisticated understanding of fluid dynamics reached another pinnacle with the Romans, whose aqueduct blueprints are marvels of pragmatic engineering. While we picture their towering arcades, the real innovation was often hidden in the details of pressure management. When an aqueduct channel needed to cross a deep valley, a simple gravity-fed arcade would have had to be impossibly high to maintain the gentle slope. The Roman solution was the inverted siphon. Their plans show they understood that water in a sealed lead pipeline could be forced up a slope after descending a downslope, as long as the outlet was lower than the inlet. They calculated the immense pressures involved and built robust lead pipelines reinforced with stone housings called casella to handle the force. This application of principle, using the weight of the water itself to push it back up, shows a theoretical grasp of hydrodynamics that wouldn't be formally equaled for over 1,000 years. The tragedy and the most telling part of this story is what happened when this centralized knowledge disappeared. With the collapse of the Roman Empire, the institutional structure that trained these hydraulic engineers and maintained these systems fractured. The detailed manuals on maintaining aqueduct gradients or repairing siphon pipes were lost or could no longer be understood. The same fate befell the Persian Qanat systems. As political order broke down, the specialized guilds of mukanis scattered, and their hard-won surveying secrets faded from memory. The result was a catastrophic regression. European cities that had enjoyed clean running water and public baths for centuries found themselves relying once more on polluted local wells and rivers, leading to repeated outbreaks of waterborne disease. It was a stark demonstration that engineering knowledge is not a one-way street toward progress. It is a fragile, living tradition that requires a stable, knowledgeable society to sustain it. The loss of these water management blueprints didn't just mean the loss of convenience. It meant the loss of health, of agricultural abundance, and of a fundamental pillar of urban civilization for hundreds of years. Perhaps no ancient structures ignite the imagination quite like the megalithic wonders built from stones so massive they seem to defy the very laws of physics. The trilithon at Baalbek in Lebanon is a perfect example. 3 limestone blocks, each weighing an estimated 800 tons, positioned high in a wall with such precision that the joints are virtually invisible. To put that into perspective, that's the weight of 2 fully loaded jumbo jets, lifted nearly 20 feet into the air and slotted together like pieces of a puzzle. The quarries where these behemoths were cut lie almost a mile away, with one even larger block, known as the Stone of the Pregnant Woman, still sitting there, partially detached from the bedrock, weighing an astonishing 1,000 tons. The sheer scale of these operations forces us to ask not just how they were moved, but how such a project was even conceived and planned. The absence of any comprehensive written blueprint from the site is deafening, but it doesn't mean the planners left no clues at all. Scattered evidence points to a system of planning that was both ingenious and practical. At sites like Sacsayhuaman in Peru, we see the final, breathtaking product: stones weighing over 100 tons, carved with bizarre, complex angles that interlock perfectly with their neighbors in a sprawling, zig-zagging wall. While no parchment plans have survived, the stones themselves are their own blueprints. The intricate, multi-faced cuts are a form of three-dimensional instruction manual. Each unique shape could only fit in one specific location, meaning the master architect's plan was translated into a numbering or coding system for the stonemasons. Furthermore, smaller scale models have been found. The Inca are known to have created clay maquettes to plan their structures, and in Egypt, a limestone ostraca was discovered that appears to be an architect's trial run, a detailed sketch of the precise angles and niches for a complex wall, drawn directly onto the flake of stone before the real work began. These were the working documents, the tangible expressions of a grand design. The methods for moving these titans remain the core of the mystery, and the fragmentary clues we have are tantalizing. A relief in the tomb of the ancient Egyptian nobleman Jehutyhotep depicts a massive alabaster statue being transported on a sledge by 172 men. A figure standing on the front of the sledge pours a liquid onto the ground in front of it, a detail long thought to be a ceremonial offering. However, modern physicists have proposed this might be the key. Water poured onto sand drastically reduces friction, effectively creating a slippery surface that would make pulling such a load exponentially easier. This single carving could be a snapshot from a lost instruction manual, a vital piece of the logistical blueprint. Similarly, the concept of acoustic levitation, described in various legends and later colonial accounts, suggests the use of sound waves of a specific frequency to somehow reduce the effective weight of a stone. While this sounds like pure myth, experiments in modern acoustic standing waves have proven that tiny objects can indeed be suspended in mid-air. Whether this technology was within the grasp of ancient builders is highly speculative, but it underscores a vital point. Our inability to replicate their feats with the tools we think they had suggests our understanding of their technical repertoire is profoundly incomplete. This gap between the achievable and the impossible is what fuels the most enduring speculation. The logical conclusion for many is that a critical component of their engineering knowledge, the core chapter of their blueprint, so to speak, has been completely lost to time. This might not have been a magical technology, but something entirely rational that simply didn't survive the collapse of their civilization. Perhaps it was an advanced form of leverage using woven ropes and wooden cranes that have long since rotted away, leaving no archaeological trace. Maybe it was a sophisticated social organization and a command of logistics that allowed them to coordinate thousands of workers with the efficiency of a modern-day project management team. The most extreme theories point to non-human sources, but this often says more about our own underestimation of ancient human ingenuity than it does about aliens. The true mystery of the megaliths isn't necessarily the lack of a plan, but our failure to find the specific, practical, and undoubtedly human instructions that turned a visionary's drawing into a reality of unimaginable scale. The stones stand as a permanent challenge, a silent dare from the past, waiting for us to finally decipher the method behind their monumental madness. What's truly sobering about these examples is that they represent more than just isolated secrets. They point to the systematic collapse of entire systems of knowledge. The Roman concrete formula wasn't just a single recipe misplaced. It was part of a vast, interconnected network of expertise. The empire maintained a dedicated core of military engineers, the architecti, who were trained in standardized methods. They had state-supported quarries producing the specific volcanic ash, a transportation network to ship it to construction sites, and apprenticeship systems to pass the knowledge to the next generation. When the political and economic structures of the empire fragmented, that entire support system crumbled. The knowledge didn't just get lost, the very profession that understood and valued it ceased to exist in its organized form. Building projects became smaller, more local, and used readily available materials like timber and rubble. The sophisticated chemical knowledge of pozzolanic reaction became irrelevant, a forgotten secret of a more advanced age. This demonstrates that advanced engineering isn't just about having the information. It's about having a society stable and specialized enough to need it, produce it, and transmit it. The case of Greek fire, or sea fire as the Byzantines called it, is perhaps an even starker example of how tightly guarded and vulnerable this knowledge was. Historical accounts describe a terrifying weapon that could be sprayed from tubes on ships, burning even on water and sticking to surfaces, making it nearly impossible to extinguish. Its precise formula was a state secret of the highest order, known only to a very select few, possibly even within a single family. It's believed the secret died with the fall of Constantinople in the 13th century. This extreme secrecy, while a powerful military advantage, was also its greatest weakness. By concentrating the knowledge in so few hands, the Byzantines made it incredibly fragile. There was no backup, no distributed network of understanding. Once those few custodians were gone, the technology vanished forever. This presents a painful paradox. The most valuable knowledge was often the most closely guarded, and therefore the most likely to be completely lost in a catastrophe. This pattern of disappearance forces us to reconsider the very nature of progress. We often imagine human history as a steady, upward climb, each generation building on the last. But the evidence from these lost technologies suggests our history is more like a stock market graph, full of sharp peaks and devastating troughs. A society can reach an astonishing peak of innovation in a specific field, like hydraulic engineering or material science, and then that knowledge can simply evaporate due to war, plague, economic collapse, or simply a shift in priorities. The Dark Ages that followed the Roman Empire weren't dark because people became less intelligent. They were dark because the complex, specialized institutions that housed advanced knowledge disintegrated. The library that held the manuals burned, the guild that trained the masters disbanded, the trade routes that supplied the special materials were cut off. We are left with the haunting ruins, the cryptic fragments of recipes, and the legends of impossible devices, all pointing to a simple, profound truth. Knowledge is not a permanent possession. It is a flame that must be constantly tended, carefully passed from hand to hand, and protected by a society that understands its value, lest it flicker and die, leaving future generations to start the long climb all over again. This process of reverse engineering the past is where modern technology truly opens a window into the ancient mind. Using three-dimensional laser scanning and ground-penetrating radar, researchers can create incredibly detailed digital models of ruins, allowing them to see patterns and relationships that are invisible to the naked eye. From this cloud of data, they can then work backwards, virtually stripping away centuries of damage and decay to reconstruct the original, pristine structure. But the real magic happens next. They can begin to test the building's performance, running sophisticated simulations to analyze how it would have handled stress, weather, and even sound. It's through this digital archaeology that we're not just guessing about ancient capabilities, we're starting to prove them. A stunning example of this is the work being done on the great ziggurats of Mesopotamia. These massive stepped pyramids, often described as mountains linking earth and heaven, were made of sun-dried mud brick, a material extremely vulnerable to the rare but torrential rains of the region. For over a century, archaeologists wondered how they survived even a few seasons, let alone millennia. The answer emerged from theoretical reconstructions. By creating detailed digital models and simulating water flow, engineers discovered that the ziggurats were designed with a hidden internal anatomy. Deep within their cores, they found evidence for what can only be described as a sophisticated drainage system: layers of baked brick and bitumen, strategically placed gravel, and carefully angled weep holes that would have channeled water away from the vulnerable core and safely out through the sides. The ancient blueprint, lost to time, was a masterclass in hydrological engineering, preserving the spiritual heart of the city from the very element that should have destroyed it. The ancient Greeks demonstrated a similar, though very different, mastery of environmental physics in their theaters. Everyone who has visited the theater at Epidaurus remarks on its perfect acoustics. A whisper from the center of the orchestra circle can be heard clearly in the very back row, high up and hundreds of feet away. For a long time, this was attributed to fortunate accident or the slope of the land, but digital acoustic modeling has revealed a far more intentional design. The precise curvature of the seating, the exact angle of the steps, and even the material composition of the limestone seats all work in concert to filter out low-frequency background noise like the murmur of the crowd, while simultaneously amplifying the higher frequencies of the human voice. The virtual blueprint shows this wasn't a happy coincidence. It was a calculated acoustic filter. The architects understood the principles of sound wave reflection and interference on an intuitive, practical level, designing an experience that was as scientifically brilliant as it was artistically profound. What these theoretical reconstructions ultimately reveal is a radical shift in our perception. We often compartmentalize ancient people, viewing their engineering triumphs as separate from their spiritual or social pursuits. But the digital blueprints show these aspects were seamlessly fused. The ziggurate's drainage system wasn't just practical, it was a metaphysical necessity, protecting the sacred connection to the gods. The theater's acoustics weren't just about clarity, they were about community, ensuring every citizen, regardless of social standing, could fully participate in the shared civic ritual of drama. The modern concepts of user-centric design and environmental sustainability weren't invented in the 20th century. They were being applied with breathtaking sophistication thousands of years ago. These reconstructed plans are more than just technical drawings. They are the rediscovered fingerprints of a holistic way of thinking, where solving a practical problem was never just about the physics of materials, but always in service of a deeper human and spiritual need. This deep integration of the sacred and the structural meant that an ancient blueprint was far more than a simple set of construction documents. It was a metaphysical map, a set of instructions for building a machine that would facilitate a connection between the human and the divine. The architect's role was therefore that of a mediator, tasked with translating abstract spiritual concepts into tangible, physical form. This required a mind that could operate with equal fluency in the languages of geometry and theology, of material stress and mystical symbolism. The blueprint was the point where these two worlds converged, and its complexity was a direct reflection of this dual purpose. A design wasn't considered successful merely because it stood up. It had to spiritually resonate, to feel right according to a deeply ingrained cultural and religious worldview. We see this principle articulated with breathtaking clarity in the Vastu Shastras, the ancient Indian texts on architecture and design. these manuals are not simply about where to place a load-bearing wall. They provide exhaustive instructions for the entire process, starting with the ritual purification of the land and the selection of an auspicious astrological moment to break ground. The central organizing principle of a Hindu temple's blueprint is the Vastu Purusha Mandala, a complex geometric diagram that represents the cosmic being, the Purusha, imposed upon the earth. The temple's entire layout, the position of its gates, the height of its towers, the number of pillars in its hall, is derived from this sacred grid. Each square within the mandala is associated with a specific deity, a specific aspect of the cosmos, and a specific function. The architect wasn't just designing a building, they were constructing a microcosm, a perfect ordered universe in stone meant to align the worshipper with the fundamental harmony of creation. This fusion of number and narrative reached another pinnacle in the soaring heights of European Gothic cathedrals. The master builders who drafted their plans were deeply immersed in a Christian worldview that saw mathematics as a divine language, a way to perceive the mind of God. Consequently, the proportions of their cathedrals were not arbitrary. They were meticulously calculated using sacred ratios and biblical numerology. The number 3, representing the Holy Trinity, might dictate the division of the nave. The number 12 for the 12 apostles could determine the number of pillars in a chapel. The use of the golden ratio, believed to be a key to divinely inspired beauty, governed the relationships between a window's height and width or the sweep of an arch. A worshipper might not consciously recognize these mathematical relationships, but the builders believed these perfect proportions would subconsciously elevate the soul, creating a space that felt inherently harmonious, ordered, and holy. The blueprint was a mathematical prayer, and the finished cathedral was that prayer rendered in light and stone. This sacred encoding of knowledge may have been one of the most effective long-term preservation strategies ever devised. By embedding advanced engineering principles within a religious framework, this knowledge was granted a form of immortality. A purely technical manual on Roman concrete might be discarded after the fall of the empire as irrelevant to a simpler, poorer society. But the design of a cathedral or a temple was sacred. Its form was considered divinely sanctioned, and to alter it was tantamount to heresy. This created a powerful incentive for conservative replication. For generations, builders would faithfully copy the established forms and proportions, even if the original reason for those proportions, the underlying mathematical or physical principle, had been forgotten. They built it that way because it had always been built that way, and because it was holy. In this way, the spiritual shell protected the scientific kernel of the knowledge for centuries, allowing it to be passed down until a future age was ready to rediscover and understand the engineering genius hidden within the sacred geometry. The survival of these techniques was not in spite of their complexity, but because of their profound cultural and religious significance. This enduring influence is perhaps most visibly set in stone, quite literally, in the very bones of our modern cities. Look at any major railway bridge from the 19th century or a grand civic building, and you will see the unmistakable signature of the Roman arch. The Romans didn't invent the arch, but they perfected its use as a structural powerhouse, understanding how to distribute immense weight down through the curved stonework and into the supporting piers, creating spans that were both strong and stunningly elegant. Their blueprints for aqueducts and amphitheaters were, in effect, the first textbooks on compressive strength and load-bearing mechanics. Modern civil engineers still operate on these same fundamental principles, using reinforced concrete and steel to achieve what the Romans did with voussoirs and keystones, proving that a brilliant structural solution is timeless. The legacy of those ancient architects is literally supporting the infrastructure of our daily lives. from the subway tunnels we travel through to the dams that hold back our water. Beyond raw strength, the ancient world also mastered the art of efficiency and environmental integration, lessons we are only now fully appreciating. The Persian windcatchers or badgers are a perfect case study. These ingenious tower structures, often detailed in surviving architectural plans, captured cool, prevailing winds at a height and funneled them down into the heart of a building, simultaneously drawing warm air up and out through a clever system of internal ventilation shafts. This created a natural, energy-free form of air conditioning that made life bearable in the desert heat. Today, in an era obsessed with reducing our carbon footprint, sustainable architects are actively looking back to these ancient blueprints. The principles of passive cooling and heating, of designing buildings to work with their local climate rather than fighting it with massive HVAC systems, are direct revivals of this ancient wisdom. Modern green buildings with their atrium ventilation, thermal mass, and strategic orientation are, in many ways, rediscovering the intuitive bioclimatic design that Persian engineers encoded into their city plans centuries ago. Perhaps the most profound modern application lies in the realm of resilience and durability, where the secrets of ancient materials are finally being decoded in laboratories. For decades, the longevity of Roman maritime concrete was a frustrating mystery. Our modern ports built with advanced formulas crumble in saltwater within decades, while Roman breakwaters have grown stronger over 2 millennia. As we discussed, the secret was the use of specific volcanic ash. But this historical curiosity has now sparked a revolution in materials science. Geologists and engineers, inspired by Vitruvius's ancient recipe, are developing a new generation of self-healing concrete. By deliberately designing mixtures that encourage the growth of mineral crystals to seal microcracks, they are creating longer-lasting, more durable infrastructure that requires less maintenance and has a far smaller environmental impact over its lifetime. This isn't mere historical imitation. It's using cutting-edge science to reverse engineer and then improve upon an ancient formula, turning a 2,000-year-old blueprint into a solution for 21st century sustainability challenges. This process of looking backward to move forward fundamentally changes the narrative of innovation. It dismantles the arrogant notion that all progress is linear and that older must mean more primitive. Instead, it reveals a vast, untapped library of human ingenuity, a collection of proven solutions to problems of scarcity, sustainability, and resilience that we are only just beginning to face on a global scale. The study of these lost civil engineering feats is no longer a niche academic pursuit. It has become a critical field of research for forward-thinking engineers and urban planners. They are poring over scans of Mayan water management systems to address modern drought, studying the earthquake-resistant pagodas of Japan to design safer skyscrapers, and looking at the integrated urban planning of ancient Mesopotamian cities for insights into creating more livable, efficient metropolises. The architects that never were are finally getting the recognition they deserve, not as mystical figures from a lost golden age, but as brilliant practical problem solvers whose work speaks directly to our future. Their blueprints are no longer relics, they are a challenge, an invitation to build a world that is as durable, efficient, and harmonious as the one they once envisioned. This tension between established history and extraordinary speculation is one of the most dynamic and, at times, frustrating aspects of studying these ancient plans. When we're confronted with a structure like the Great Pyramid, whose precision and scale seem to push against the boundaries of what we believe was possible with copper tools and human labor, a vacuum of explanation forms. And into that vacuum rush a host of alternative theories, from the intriguing to the outlandish. The most persistent of these is the ancient astronaut hypothesis, which suggests that the blueprints for such marvels were given to early humans by visiting extraterrestrials. This idea often points to the sheer ambition of the projects and certain artistic interpretations of figures that some claim resemble astronauts or advanced technology. Similarly, the myth of Atlantis, a technologically superior civilization lost to the sea, is often invoked as the source of this lost knowledge. While these narratives are compelling on a science fiction level, they share a critical flaw. They don't actually explain anything. Instead, they simply replace one mystery with another, substituting "How did humans do this?" with "How did aliens do this?" More importantly, they fundamentally underestimate the ingenuity, patience, and profound intelligence of our ancestors, effectively robbing them of credit for their own achievements. A more grounded but equally fierce debate revolves around whether certain ancient diagrams were ever intended to be practical construction guides at all. Take, for instance, the intricate geometric patterns found in some medieval manuscripts, or the symbolic layouts described in texts like Plato's account of Atlantis. Are these the literal blueprints for a city, or are they philosophical and cosmological diagrams meant to illustrate an ideal of harmony and order? Scholars often clash over this very point. Some see in these designs a coded mathematical language for actual engineering, while others argue they are purely allegorical, a way of using architecture to talk about the nature of the universe and humanity's place within it. This isn't a trivial distinction. Interpreting a symbolic map as a literal one can lead to wild goose chases for sunken cities that never existed in a physical form, while dismissing a practical guide as mere symbolism could cause us to overlook a genuine technical manual. The truth likely often lies in a blend of both, as we've seen with structures that served both a physical and a profound spiritual purpose, their blueprints acting as guides for both the mason and the priest. Navigating this landscape requires a disciplined and careful approach. Healthy skepticism is the engine of good historical science. It's what drives researchers to question old assumptions, demand evidence, and seek out new interpretations. This is how we eventually decoded the Antikythera Mechanism and discovered the self-healing properties of Roman concrete. However, this must be balanced against a dismissive cynicism that rejects any new idea simply because it challenges the conventional timeline. The real work happens in the painstaking middle ground, where archaeologists, engineers, and historians collaborate to test hypotheses against the physical evidence. They use tools like lithic analysis to study the wear patterns on ancient stone cutting tools, or they build scale models to see if a proposed method for moving megaliths actually works with the technology of the time. This process is slow, methodical, and rarely produces headline-grabbing revelations about aliens or lost super-civilizations. But what it does produce is something far more valuable: a gradually deepening, evidence-based appreciation for the authentic and human genius of the ancient world, a genius that is remarkable enough on its own without needing any extra help from beyond the stars. Perhaps the most direct conversation between an ancient blueprint and its environment is found in the sprawling city plans of the Indus Valley civilization, such as Mohenjo-Daro and Harappa. These metropolises, flourishing over 4,000 years ago, were designed with a sophistication that would impress a modern urban planner. Their grid-like street layouts weren't just for order. They were a deliberate response to the region's dominant wind patterns, strategically oriented to create natural ventilation corridors that channeled cool air through the entire city, mitigating the intense heat. But the real engineering marvel lay beneath the streets. Archaeologists have uncovered incredibly detailed civic blueprints focused on water management, featuring a vast network of baked brick drains, covered sewers, and even individual wells for houses. These systems were designed with a precise gradient to ensure waste was efficiently carried away, protecting the population from waterborne diseases. This wasn't a reactive system. It was a proactive, master-planned infrastructure that demonstrates a profound understanding of hydrodynamics and public health, showing that their architectural vision extended far beyond single buildings to encompass the entire well-being of the community in a specific climatic context. This principle of designing with the land rather than against it reaches its zenith in the breathtaking Andean terraces of the Inca. The blueprints for these structures were not drawn on parchment but were etched into the very mountainsides they transformed. Faced with the dual challenges of intense rainfall and steep, erosion-prone slopes, Inca engineers designed a system of steps that appears deceptively simple. However, each terrace was a complex geoengineering project. The plans, likely encoded in the knot language of the Quipu, would have specified the construction of deep gravel foundations for drainage, the precise angle of the retaining walls to withstand seismic activity, and the selection of different soil types layered to create optimal growing conditions. These were not just farms, they were massive, sculpted landscapes that controlled water flow, prevented catastrophic erosion, and created microclimates allowing for the cultivation of a diverse range of crops at different altitudes. The loss of this intricate, place-specific knowledge after the Spanish conquest had immediate and devastating consequences, as imported European farming techniques proved disastrously unsuitable for the rugged Andes, leading to widespread soil loss and famine. The terraces stand as a stark lesson in the value of designs born from a deep, generations-long dialogue with a specific place. The counterpoint to this success story is the tragic loss of such place-based knowledge, which often occurred when empires collapsed or cultures were subsumed. With the fall of the Roman Empire, the intricate blueprints for maintaining their vast water networks, the precise gradients for aqueducts, the repair techniques for inverted siphons, were lost alongside the centralized administration that valued them. European cities that had enjoyed clean, running water for centuries found themselves reverting to drawing water from polluted local wells and rivers, leading to recurrent epidemics of cholera and typhoid for hundreds of years. This regression wasn't due to a lack of intelligence, it was a catastrophic data-loss event. The specialized profession of the Roman hydraulic engineer vanished, and the sophisticated environmental knowledge embedded in their civil engineering projects became obsolete, replaced by a simpler, more desperate mode of survival. This pattern repeats itself throughout history, illustrating that technological progress is not a one-way ascent but a fragile continuum that can be broken, leaving societies vulnerable to the very environmental challenges their ancestors had so brilliantly overcome. What makes these ancient environmentally attuned designs so relevant today is that they represent a masterclass in sustainable resilience achieved through observation and adaptation, not brute force technology. The Persian badger or wind catcher is a perfect example. This ancient form of air conditioning, detailed in architectural plans for centuries, required no electricity, only a sophisticated understanding of fluid dynamics and local wind patterns. The structure captured cool, prevailing breezes at a height and funneled them down into the building's interior, simultaneously drawing warm air up and out through ventilation shafts. This created a comfortable, energy-free living environment in some of the world's hottest climates. Modern architects are now looking back to these very principles, designing buildings with atrium ventilation, thermal mass, and strategic orientation to drastically reduce reliance on energy-intensive HVAC systems. In this way, the ancient blueprint is no longer a relic. It has become a vital source of inspiration, offering proven, time-tested solutions for creating a built environment that doesn't fight the natural world but works in concert with it, promoting sustainability and harmony for generations to come. But this conversation about lost knowledge leads us to a crucial and often overlooked question. Who were the individuals actually holding these blueprints? For centuries, the image of the ancient master builder has been overwhelmingly male, a bearded figure in robes directing armies of laborers. However, a quiet revolution is underway in archaeology and historical research, one that is meticulously piecing together a very different and far more inclusive picture. Scattered evidence is emerging that women were not merely passive observers in these ancient feats of engineering. They were active participants, overseers, and perhaps even the masterminds behind some of the most enduring structures ever created. This isn't about rewriting history to fit a modern narrative. It's about finally reading the full record that has been there all along, waiting for us to look past our own assumptions. Consider the case of ancient Egypt, a civilization renowned for its meticulous record-keeping. While the grand monuments are often attributed to pharaohs and their chief ministers, the day-to-day reality of these massive projects was managed by a complex bureaucracy of scribes and overseers. And among the thousands of administrative documents, ostraca, and tomb inscriptions, we find the names of women in positions of significant authority. There are titles like Overseer of the Craftsmen or Overseer of the Royal Works attached to female names. For instance, the blueprint or plan for a significant temple or tomb complex wouldn't just materialize. It would be executed under the watchful eye of such an overseer, someone responsible for coordinating materials, labor, and adherence to the sacred geometrical specifications. These women weren't just occasional anomalies. They appear to have been integrated into the professional class responsible for turning architectural visions into stone and mortar. Moving to Mesopotamia, the cradle of civilization with its vast ziggurats and advanced urban planning, the cuneiform tablets tell a similar story. These clay documents, which served as everything from receipts to legal contracts, reveal women were deeply involved in the economic and managerial engine of construction. They are recorded as owning and operating the very workshops that produce the critical materials for building projects' brick factories, for example. Controlling the production of bricks meant controlling the primary building block of an entire civilization. A woman who owned such an enterprise wouldn't just be a supplier. She would have been a vital partner in the construction process, likely consulted on quantities, quality control, and delivery schedules essential for keeping a project on track. Furthermore, tablets mention women acting as surveyors of land and even as managers of large workforces, roles that required not only literacy and mathematical skill, but also significant executive authority. So why has this narrative been missing for so long? The answer lies in the layers of interpretation that have been applied over centuries. Later historians, often working from their own cultural perspectives where certain professions were gendered, may have encountered these titles and automatically assumed they belonged to men, or they simply dismissed the evidence as insignificant. The physical work of archaeology itself was also a field dominated by men for generations, and it's possible that the subtle clues pointing to female involvement were simply not the focus of their inquiry. We are now in an era where a new generation of researchers is asking different questions and examining these ancient records with a fresh perspective. And what they are finding is fundamentally altering our understanding of the social dynamics behind these engineering marvels. This recalibration of history does more than just fill in missing pages. It has a profound impact on our present and future. By acknowledging that technological prowess and engineering genius were not the exclusive domain of one gender in the ancient world, we shatter a persistent and limiting stereotype. It demonstrates that the ability to conceptualize, manage, and build is a human trait, not a masculine one. For a young girl today fascinated by how things are built, knowing that women were overseers on the projects that created the pyramids is incredibly powerful. It provides a lineage, a sense of belonging in a field where they might have felt like an outsider. This recovered history argues for a more diverse and inclusive approach to the engineering challenges we face today, suggesting that the best solutions come from harnessing the full spectrum of human talent and perspective, just as some of the greatest civilizations of the past appear to have done. The loss of these narratives was itself a kind of historical catastrophe, but their recovery offers a blueprint for building a better, more equitable future. Today, the process of unraveling these mysteries is undergoing a revolution, not with shovels and brushes, but with lasers and algorithms. The field of digital archaeology is fundamentally changing how we interact with these ancient plans, allowing us to step inside the minds of long-lost engineers in ways that were once pure fantasy. Using high-resolution, three-dimensional laser scanning and photogrammetry, researchers can create incredibly detailed digital twins of fragile artifacts, from cracked clay tablets to faded parchment fragments. This means a blueprint etched on a piece of limestone that would crumble if touched can now be studied, rotated, and magnified from every conceivable angle on a computer screen, preserving the original while revealing its secrets. This non-invasive approach is like giving historians a superpower, the ability to see the unseen without risking a single irreplaceable relic. The true magic happens in the digital reconstruction phase. Often, we don't have a complete blueprint, we have pieces. A corner of a temple layout here, a segment of an irrigation channel there. Advanced software can now take these scattered fragments and, like solving the world's most challenging jigsaw puzzle, begin to fit them together virtually. Algorithms can search for matching fracture lines, align faded ink strokes, and even predict missing sections based on the symmetry and patterns of the existing pieces. For instance, by scanning dozens of disparate fragments of Roman architectural plans found at sites like the ancient city of Pergamon, researchers have been able to digitally reassemble them, revealing the complete layout of a building or a complex water system that was previously only understood in disconnected parts. This process can uncover critical details that were invisible to the naked eye, such as tiny notations for specific materials or subtle lines indicating load-bearing walls. But digital archaeology goes far beyond simple reassembly. It allows for dynamic testing and simulation, transforming historical speculation into empirical analysis. Once a structure is digitally rebuilt from its blueprint, engineers can run it through a virtual gauntlet of stresses. They can simulate the force of hurricane winds on a Mayan pyramid, model the flow of water through a Roman aqueduct's inverted siphon, or apply the seismic shockwaves of an earthquake to an Inca wall. These simulations answer practical questions that have puzzled us for centuries. How did this temple not collapse under its own weight? Exactly how much water could that canal system deliver to a city? By seeing how the virtual model behaves, researchers gain profound insights into the practical challenges the original builders faced and the ingenious solutions they devised. It moves the conversation from "how did they build this" to "why did they build it this way?", revealing the nuanced engineering principles embedded within the design. This powerful synergy between cutting-edge technology and ancient intellect is creating a new dialogue across the centuries. We are no longer just passive observers of the past. We are active participants in a grand experiment of reverse engineering. Every scan, every simulation, and every digital reconstruction adds another piece to the puzzle, allowing us to appreciate the breathtaking full scope of ancient innovation. We can now witness a building rise from its foundations not as a ruin, but in its intended glory, and understand the complex calculations that made it stand. This isn't just about admiring their achievements, it's about finally being able to read their engineering language, a language of resilience, sustainability, and brilliance that has been waiting silently in stone and clay for millennia to be understood once more. But this incredible power to reconstruct and reclaim lost knowledge comes with a profound and often overlooked responsibility. As we gain the ability to read these ancient blueprints with greater clarity, we must also learn to read the ethical lines that surround them. This isn't just an academic exercise, it's a moral imperative. The drive to uncover every secret of the past can sometimes trample on the very living cultures for whom this knowledge is not a historical curiosity, but a sacred and vital part of their present identity and heritage. Consider a scenario that is playing out in boardrooms and laboratories right now. A modern corporation funds research into traditional building techniques or ancient herbal remedies. Their scientists isolate the active compound or reverse engineer the structural principle, and then they patent it. Suddenly, a knowledge system developed and safeguarded by a community over countless generations becomes the intellectual property of a distant company, which can then charge that same community for access to the very wisdom it created. This isn't a theoretical problem. It's a form of biopiracy and cultural appropriation that has happened with everything from medicinal plants to specific weaving patterns. When the blueprint is for something as tangible and valuable as self-healing concrete or earthquake-resistant architecture, the financial and ethical stakes are immense. The question is not just can we use this knowledge, but should we, and if so, on what terms? Does the mere act of decoding a secret give us the right to exploit it, or does a portion of the benefit rightfully belong to the descendants of its original architects? This dilemma becomes even more sensitive when the knowledge in question is explicitly sacred or secret. Many ancient blueprints were not merely technical documents. They were spiritual maps, their full meaning accessible only to initiated elders or specific guilds. For some indigenous communities, certain architectural forms, astronomical alignments, or even the act of building itself are woven into their most sacred ceremonies and creation stories. The unrestrained scientific dissection of these practices, even with the best intentions, can feel like a profound violation. It risks reducing a living, breathing spiritual tradition to a set of data points, stripping it of its context and its soul. The imperative then shifts from pure discovery to respectful dialogue. It requires researchers to approach these communities not as subjects to be studied, but as partners and custodians whose consent and collaboration are essential. This means sometimes accepting that some doors should remain closed, that some knowledge is meant to be preserved, not published. Navigating this complex landscape requires a fundamental shift in how archaeology and historical research are conducted. The old model of the outsider expert arriving to extract artifacts and information is increasingly being replaced by a framework of community-based participatory research. This means involving descendant communities from the very beginning of a project not as informants, but as co-directors of the research questions, the methodologies, and the outcomes. It means following established ethical guidelines that prioritize free, prior, and informed consent, ensuring that communities understand the scope of the work and have the power to say no. It also means committing to tangible benefit sharing, whether that involves repatriating culturally significant artifacts, creating educational programs for community youth, or ensuring that any commercial applications of rediscovered knowledge include fair compensation and recognition. This mindful, collaborative approach transforms the process from one of extraction to one of exchange. ensuring that the quest to understand the architects of the past is conducted with the dignity and respect they deserve, and that their living heirs are finally given a voice in telling their own story. Looking ahead, the potential for discovery feels almost limitless as our technological eyes and ears grow ever more powerful. Ground-penetrating radar and LiDAR are already peeling back jungle canopies and desert sands to reveal the ghostly outlines of entire cities we never knew existed. And with each new map, the chance of uncovering a sealed repository of knowledge, a true ancient architect's library, grows more tangible. Imagine a scenario where we don't just find another fragmented clay tablet, but an entire archive, a room filled with the rolled-up papyrus or vellum plans for structures that have either completely vanished or that we've only ever misunderstood. The most tantalizing targets for such a find might be the legendary Hanging Gardens of Babylon, a wonder whose very existence and mechanics remain a subject of debate. A genuine blueprint could finally settle the mystery, revealing the sophisticated hydraulic pumps and irrigation systems that would have been needed to create such a marvel in the heart of a desert metropolis. Beyond the terrestrial, our gaze is also turning to the world's coastlines and shallow seas, where countless ancient settlements are known to have been submerged by rising water levels at the end of the last ice age. The discovery of even a single well-preserved structure, like a sunken temple complex off the coast of India or a Neolithic village in the North Sea, could offer an unprecedented snapshot of prehistoric engineering. The blueprints for these places wouldn't be on paper, they would be the structures themselves, perfectly preserved in anoxic mud, offering a complete curriculum in ancient materials science, foundation laying, and adaptation to challenging environments. This isn't just about finding lost cities, it's about accessing a frozen moment in time, a preserved classroom of techniques that were lost when the waters rose and the survivors were forced to adapt and, in the process, perhaps forget. The tools for unlocking these secrets are also evolving at a breathtaking pace. Artificial intelligence is now being trained to recognize patterns in ancient languages that have stumped scholars for centuries. I could cross-reference thousands of fragmented inscriptions, architectural details, and known construction techniques from across the globe to suggest translations for untranslated scripts like Linear or the Indus Valley script. If these scripts contain even passing references to engineering principles, the impact would be revolutionary. Furthermore, international collaborations are breaking down old barriers, allowing experts from diverse fields, from materials scientists to astrophysicists, to examine ancient problems with a fresh perspective. A structural engineer might look at the cracks in a megalithic wall and deduce the exact sequence of its construction, while a geologist could trace the quarry sources of stones to reconstruct ancient trade routes used to transport building materials, effectively reverse engineering the logistical blueprints that made these projects possible. This isn't merely an academic exercise to satisfy historical curiosity. It has profound practical implications for our own future. The challenges of climate change, particularly rising sea levels and more frequent extreme weather events, demand resilient and sustainable infrastructure. Ancient civilizations often excelled at building in harmony with their environment, not in opposition to it. Discovering the blueprints for the sophisticated water catchment systems of the Nabateans, who built a civilization in the hyper-arid desert of Petra, could inspire new approaches to water conservation in drought-stricken regions today. Similarly, understanding the seismic dampening techniques perfected in Japanese pagodas over 1,000 years ago could directly inform the design of earthquake-resistant skyscrapers in modern mega-cities. The past becomes a living laboratory, offering a catalogue of proven, time-tested solutions to problems we are only now coming to fully appreciate. The most exciting prospect is that the next great discovery might not even be on our current radar. It could be a set of plans for a machine described only in myth, like Archimedes' heat ray or Heron's steam engine, found in a long-forgotten monastic library. It could be the complete astronomical observations of a culture like the Dogon, whose oral traditions contain surprisingly accurate knowledge of celestial bodies invisible to the naked eye, suggesting a lost science of optics and observation. Each new fragment of the puzzle brings us closer to those anonymous masterminds, the architects whose names are lost to history but whose legacy is written in stone, water, and the very alignment of the stars. Their story is ultimately a story about the resilience of human ingenuity itself, a reminder that brilliance can flourish, be lost, and patiently wait in the soil for a future generation to come along, ready to listen and learn from the blueprints they left behind. Perhaps the most powerful lesson these ancient plans offer is a masterclass in holistic thinking, a radical departure from the hyper-specialization that often defines modern engineering. Today, an architect might design a building's form, a structural engineer ensures it stands, a mechanical engineer designs its climate systems, and an environmental consultant assesses its impact, all working in separate silos. The master builders of the past operated with a unified vision. The Egyptian architect who designed a temple was also its astronomer, its theologian, and its materials scientist. He didn't just calculate the load-bearing capacity of a column. He calculated its alignment with the star Sirius and selected the specific limestone that would resonate with a certain frequency during chanting. This deep integration of disciplines wasn't a philosophical nice-to-have. It was the essential core of their practice, resulting in structures that were not only physically sound, but also culturally profound and environmentally attuned. Modern education, by reintegrating these separated fields by having structural engineers study basic astronomy and environmental scientists learn the principles of sacred geometry, could produce a new kind of innovator, one capable of designing solutions that are as elegantly efficient as they are meaningfully connected to human and ecological needs. This naturally leads to the second critical lesson, a profound, built-in ethic of sustainability. Ancient engineers didn't have the luxury of infinite resources or fossil fuels to power through design flaws. Their blueprints reveal a deep respect for materiality and a genius for energy efficiency. The Persian windcatcher or badger is a perfect example. Its design required a sophisticated understanding of local wind patterns, thermodynamics, and fluid dynamics to create natural air conditioning without a single watt of electricity. The Roman insistence on using specific volcanic ash from Pozzuoli in their concrete was a lesson in sourcing local materials with superior, long-term performance, creating an infrastructure that lasted millennia with minimal maintenance. These weren't green add-ons. Sustainability was the baseline, the fundamental constraint that drove innovation. Modern engineering education could powerfully benefit from making sustainable design the central, non-negotiable parameter of every project, not an optional supplement, challenging students to see resource constraints not as a limitation but as the very source of their most creative solutions. Furthermore, these ancient case studies serve as the ultimate cautionary tales about the fragility of knowledge itself. The story of Roman concrete is not just about a lost recipe. It's about the collapse of the entire ecosystem that supported it, the trained architecti, the specialized quarries, the transportation networks, and the apprenticeship systems. This teaches a crucial meta lesson for modern education. Technical knowledge is not a static artifact to be possessed, but a living tradition that must be actively maintained and transmitted across generations. Engineering curricula should therefore include not just the how of building, but also the how of preserving and sharing that knowledge resiliently. This means emphasizing clear documentation, open source collaboration, and the building of diverse, redundant knowledge networks that can withstand social upheaval. It encourages engineers to see themselves as links in a long chain, responsible not only for innovation but also for stewardship, ensuring that the hard-won lessons of today do not become the inaccessible mysteries of tomorrow. By weaving these historical narratives directly into the fabric of engineering education, we do more than just add interesting context. We fundamentally reshape the mindset of future builders. Imagine a civil engineering student studying the Inca terraces at Moray, not just as an archaeological wonder, but as a complex project in geotechnical engineering, hydrology, and microclimate management. Or a materials science student reverse engineering the chemical processes within 2,000-year-old Roman maritime concrete to inspire new, self-healing composites. These case studies provide a rich library of proven, time-tested solutions to problems of resilience, resource management, and community design that are incredibly relevant to 21st century challenges. They cultivate a deep sense of humility and perspective, reminding students that they are part of a long human conversation about how to best shape our world. This approach doesn't diminish modern technology. It enriches it, providing a deeper well of inspiration and a sobering reminder that true progress is measured not just in the height of our skyscrapers, but in the enduring wisdom and resilience we build into everything we create. If this journey into the minds of ancient architects has sparked your curiosity, the incredible news is that you no longer need a time machine to explore their world firsthand. Some of the greatest repositories of this knowledge are just a short trip away. Institutions like the British Museum in London or the Louvre in Paris house breathtaking collections of original artifacts, from intricate scale models etched on clay tablets to the actual tools used by these master builders. But you don't have to travel across the globe. Many local natural history and science museums frequently host special exhibitions on archaeological wonders, bringing these ancient blueprints to life with stunning reconstructions and interactive displays that let you virtually walk through a digitally reborn Babylonian temple or a Roman bathhouse. For those who prefer to explore from the comfort of home, the digital world offers an unprecedented gateway. Numerous universities and cultural institutions have embarked on massive digitization projects, creating vast online archives where you can inspect high-resolution, rotatable 3D models of fragile papyrus plans or carved stone inscriptions. You can take a virtual reality tour of the Giza Plateau, examining the pyramid's alignment from every angle, or explore the inner chambers of the Pantheon in Rome, all with a few clicks. The Smithsonian, National Geographic, and countless archaeological foundations offer extensive online libraries, documentary series, and expert-led webinars that delve into the latest research and discoveries, making this specialized field more accessible than ever before. Perhaps the most engaging way to truly appreciate the genius of these ancient engineers is to try your hand at their craft. With modern computer-aided design software, or CAD, you can attempt to recreate their structures from the ground up. Download a scan of an ancient Greek temple plan and model it in 3D, experimenting with the weight distribution of the lintels or the angle of the columns. There's no better way to understand the challenge of designing the perfect Roman arch than to virtually build one yourself and see what happens when you adjust the keystone. This hands-on process transforms abstract admiration into a tangible appreciation for the precision and foresight required, allowing you to confront the same problems they did and marvel at their elegant solutions. Engaging with these resources does more than just satisfy a passing interest. It actively contributes to a living, evolving field of study. Every fresh set of eyes examining a digital scan of the Antikythera mechanism might notice a previously overlooked gear tooth. An amateur historian experimenting with a CAD model of an aqueduct might propose a new theory about its water flow. This collective curiosity, fueled by public access and modern technology, is itself a form of preservation, ensuring that the blueprints of the past are not just static relics in a museum case but dynamic sources of inspiration. Each person who delves into this mystery becomes part of a new generation of explorers, helping to decode the secrets of the architects that never were and ensuring their monumental legacy is never forgotten again. Ultimately, what these ancient blueprints reveal is a world of astonishing sophistication, where master architects achieved feats that still leave us in awe. Their work was not merely about piling stone upon stone. It was a profound integration of astronomy, physics, and artistry, demonstrating a technological capability that fundamentally rewrites our understanding of history's timeline. We see this in the precise cardinal alignment of the Great Pyramid, a surveying marvel achieved without modern instruments, and in the self-healing chemistry of Roman concrete, a material science formula that was lost for centuries. These were not accidental discoveries but the products of rigorous, formalized knowledge, a deep understanding of the world that was systematically applied to create structures of enduring strength and beauty. While countless secrets remain locked within undeciphered scripts and undiscovered libraries, each new technological breakthrough brings us closer to the brilliant minds behind these wonders. The ongoing work to decode the full meaning of the Inca quipu, or to virtually test the acoustics of a Greek theater, is more than just academic curiosity. It is a form of intellectual time travel. We are slowly piecing together a lost chapter of human ingenuity, one that showcases an alternative path of innovation built on harmony with the environment and a holistic view of science and spirit. This process is a humbling reminder that technological progress is not a straight, inevitable line upward, but a fragile continuum that can be fractured by time, disaster, or simply the failure to pass knowledge to the next generation. The true legacy of these architects is not just in the stones they left behind, but in the powerful lessons they offer for our own future. They teach us that engineering at its finest is not just about building bigger or taller, but about innovating sustainably, adapting to environmental challenges, and designing for resilience that spans generations. Their blueprints serve as a timeless source of inspiration, offering proven solutions for modern problems like water scarcity, seismic activity, and sustainable material use. As we face our own global challenges, looking back at their achievements provides a crucial blueprint for moving forward, one that values wisdom over mere progress and longevity over short-term gain. Thank you for joining me on this incredible journey to decode the secrets of the architects that never were. If these stories of lost innovation resonated with you, please show your support by liking this video and subscribing to the channel for more deep dives into history's greatest mysteries. I would love to hear which ancient wonder fascinates you the most. Was it the Antikythera Mechanism, the Roman aqueducts, or the mysterious walls of Sacsayhuaman? Share your thoughts and questions in the comments below, and let's keep the conversation going. Until next time, keep